Hello everyone, my name is Robert and this is the video report for Lab 1 for constant velocity. So the purpose of this lab was to observe the one-dimensional motion of an object traveling at a constant velocity without changing direction. For this we used two models. We ran an experimental model of comparing the rolling motion of an expo marker without any external forces, and then comparing that to a computational model using constant velocity from Newton's second law. So fundamental principles, of course, Newton's second law, where we're deriving the velocity update formula as well as the position update formula. And for the velocity update, for velocity to remain constant without any applied force, then we need to assume that F net equals 0 for it to remain constant. For experimental, since velocity is more difficult to measure, we are measuring or estimating velocity from the change in position instead. Whereas the computational model, we are using the constant velocity from velocity update to estimate the next position. Overall results of this experiment was that we saw that the rolling motion of the marker would track pretty closely to the computational model, but there was a little bit of deviation where the marker was slowing down, most likely due to friction, which was not accounted for in the computational model. So conceptual ideas that we're using is the definition of velocity, Rf minus Ri divided by delta t. And then from Newton's second law, we have derived the velocity update equation and position update. For our models, we are using a rolling expo marker where the marker was pushed in essentially first, and then we are only recording from the time of which it is rolling without any more external force being applied to it, and tracking position, and then comparing that to the singular motion of the computational model of just the ball moving to the right as the time frame progresses. So since there is no external force applied after the marker is initially pushed, it should continue to roll at the same velocity, meaning the same distance of position change should occur for each time interval. For the experiment itself, we designated the system to be the expo marker and the surroundings to be everything else. The table that it's rolling on, the air around it, as well as Earth applying gravity. To get the mass of the marker, we use a triple beam balance, and we set the initial conditions for it to be at the origin at the purple cross from the tracker program. And since this is more difficult to measure velocity, we are instead tracking position and then using that to estimate velocity. For the computational model, we can see our code here. The ball's mass is set to 0.01389 kilograms as taken from the experimental weigh-in. We set the origin to 0, 0, 0, and velocity is taken from the experimental as well as the very first time frame of like the 0.01 delta t, and we see that's 1.030 meters per second, and we expect it to be continuing at that rate as we go through the while loop, which is the same length as the experimental data. F net has been set to 0, and then the velocity update has been updated to reflect the velocity update equation from Newton's second, as well as the ball position update. So we're using the velocity to update the position, and velocity should remain constant as there is no applied force. So since the velocity is constant, we assume that there's no force in the x direction since nothing is pushing on it. If we consider the y direction, we have a balance between the Earth's pull of gravity and the normal force from the table, keeping the marker from falling through it. And this is the diagram of what the computational model spit out, where it is moving an object to the right or in the positive x hat direction. For our results, the computational model, we see position versus time and experimental versus time is relatively similar. They are both linear. Versus velocity versus time, the computational is perfectly flat, whereas velocity versus time and experimental has a little bit of jitter as we're measuring from position, and position has not been entirely accurate on the tracker software trying to estimate the center of mass, as well as other effects in the real world as like air resistance or friction. So this is our final graph where we see Theoretical is the orange line versus experimental the blue line. And since they are very, very close, but we do see a little bit of deviation as it curves away due to friction slowing the marker down. So from the graph, we see that the computational model is not including friction or air resistance, and we see that in the experimental model, so it's not entirely balanced directly in the x direction and is slowing down due to friction.